In this module, we are going to cover some mathematical algorithms. There are algorithms for processing data, strings, and such, but there's a number of algorithms for just crunching numbers. And if you're a Python programmer, you may be from the life sciences, where you're trying to process millions of gene sequences, or doing work in mechanical engineering, where you've got a lot of matrices that have to be multiplied. In any number of disciplines, there's a need for raw power. And what algorithms gives you is the ability to identify a problem for which the naive solution is not the optimal one. And through a little more advanced study and structuring of the problem, you can usually find algorithms that break through a barrier and give you the performance that you really need. We're going to do this in the context of identifying a simple mathematical algorithm and finding out ways to optimize that. And hopefully this will inspire you to carry out similar exercises in your own domain. They are exceptional at their ability to take a problem and demonstrate how you can get better performance. We've already seen this in our discussion about the asymptotic growth of functions. If you have an algorithm that exhibits order n squared growth, as the problem size doubles, it takes 4 times as much work to solve the problem. If you can only find a way to break that into an n log n behavior, or even linear behavior, you will have achieved tremendous improvement that makes problems that were otherwise intractable within your reach. There are so many mathematical algorithms. I've chosen one for demonstration purpose, but you should find resources that will let you identify the ones best suited for your domain. The Numerical Recipes website, and in fact all the books in that series, have identified extremely efficient, highly practical algorithms that you can put to use today. So you don't have to implement them yourself. You can take code that's been highly tuned and optimized and use it for your own purposes. We're going to cover today what would otherwise seem an impossible task and show you how to come up with a more efficient algorithm than you might believe. Consider computing x to the nth. This is known as exponentiation. When n is 2, you square the number, or it's x cubed, and so on. If you're going to compute x to the n, the naive algorithm is to do n minus 1 computations. Just take that value x and multiply it by itself n minus 1 times. How could there be any other way, you might ask? Well, if you imagine x to the 6th, and I wanted to reduce the number of multiplications, if I observe that x to the 6th is nothing more than x cubed, again squared, I've taken something that would have required 5 multiplications and turned it into something that requires only 3. That small observation might look like an oddity, but it turns out that for any n, you can identify the minimum number of multiplications to get to the result x to the n. And this is not a trivial concern. In many disciplines, most particularly cryptographic, there's a need to raise numbers to very high powers, 500 or so. And to anything we can do to take that which would otherwise be a linear algorithm and turn it into a logarithmic algorithm will give you an incredible boost of performance. And this is the reason why fundamentally cryptographic systems are both secure and efficient, because of these kind of optimizations. So let's discuss exponentiation by squaring. It's a surprisingly versatile algorithm, and in attacking this algorithm, we're going to see approaches that you could probably use in others as well. If you were tasked with computing 2 to the 13th power, most of us would just sit down on a calculator and type 2 to the 13th. But let's assume you didn't have that. You'd have no choice but to multiply 2 by itself 12 times. But what if you would instead observe that 2 to the 13th is really 2 times 4 to the 6th? Okay, does that get me anywhere? Well, I look at 4 to the 6th, and I say, well, that's really nothing more than 16 cubed. And so I'm refining the problem at every step, and I'm cutting the problem in half at every step. I started with a need to compute some number to the 13th power. And then I reduced that into a problem where I only need to compute it to the 6th power, and then the 3rd power, and finally the 1st power. And if you look at this chart, all the red multiplied stars are the only ones that I need to do. I turned in something that would have required 12 multiplications, and I reduced it to 5. The trick is, how do you identify those sub-problems that will allow you to take a larger problem and break it up into these smaller ones? And that's what exponentiation by squaring does. The pseudocode is surprisingly brief, and after we've discussed this code, we'll go in and actually look at the real code in Python. As you know, anytime you can take a problem and divide it up into smaller problems of half the size, you're on your way to a log n behavior. That's exactly what we can do here. In this spec sheet, the best, average, and worst case are all log n because it doesn't matter what exponent you're trying to raise it to. I can apply this repeatedly. There are two base cases that you would need in any recursion. Here, if I'm raising x to the 0th power, I know that it's 1. And if I'm raising x to the 1st power, I know that it's x, so I can stop it at that point. Otherwise, I have two cases to consider. What if the exponent is an odd number? What if it's an even number? So if I started with 2 to the 13th, which is an odd number, I divided that up into a problem that said, well, let me take one of those 2's out, and let me raise 4 to the 6th. What if the exponent had been an even number, like you see here? Then I don't have to do any real work. I just say 4 to the 6th is nothing more than 16 to the 3rd power. And I'm increasingly finding ways of dividing up my problem up each time through to be half the original size. You can see the recursion there. There's only one recursive step each time through, and so I rapidly converge on a solution. Let's now translate this algorithm into Python. I want to raise to a higher exponent some value x to the nth power. This is going to return the value of x raised to the nth power. In the description of the algorithm, there were two base cases. If n is equal to 0, then I know I can return 1. If n is equal to 1, then I just return x. Every recursion has to have the base case to be able to stop it, to prevent infinite recursion. At this point, I now know it's a number greater than 1. My concern is it even? Is it odd? I will use the modulo operator, which in Python is this percent sign. If n is odd, then n%2 is equal to 1, which means that this code would execute. And as you remember, I want to take that challenge, raising the power to an odd number, and break it up into half the size. And the way that we did this is we said, well, it's really nothing more than pull out one of those x's that you need to square, and instead take x squared and raise it to half the size of the original exponent. At this point, we know that n is an odd number, so n minus 1 over 2 will, of course, be a valid integer. And I pull out 1, and I do the x squared here to take a power like 2 to the 13 and turn it into 2 times 4 to the 6. Lastly, n could be an even number, in which case I can just return x squared half the power. That's all there is to it. So if I take this and run this, I can quickly determine that I can raise 2 to the 13th power and get 8192, which is the right number. You can find, surprisingly, in Python, it works quite nicely with very large numbers. And that's one of the real benefits of Python as a numerical algorithms, is that it can handle large numbers effortlessly. And we'll see that later on in today's module. So I have that, and now my question is, well, how efficient is it? Well, I need to put together some analysis to try to compare this approach with the more naive algorithm. So I'll have a small little trials. I want to demonstrate the performance. So we've used this information before. I'll get my time from the time module. And we'll start with some number. It doesn't really matter what the value of x is, to be honest. I'll just start with 999 just as an arbitrary number. And what I want to do is compute how much time it takes for the naive approach and how much time it takes for the recursive approach. And I'll do each of these trials one at a time. And for each one, I'll compute the time it takes to compute the exponent of that base raised to that power of t. And I'll remember that time in my summing up. And I'll do it as well here for the second, the more manual, naive approach. And I'll say, well, if I'm going to multiply x by itself, then I need to do it n times. And I'll start with this for I in range of t, that's my power. I'm going to say check 2 is equal to check 2 times base. This allows me to build up a product, one multiplication at a time. And when I'm done, I've got my natural time for computing that. So when I have an optimization, it is useful to sometimes check that you haven't broken the computation. So I'm going to compare check 1 and check 2, just as a matter of habit. That if they're different, I better raise an exception. Otherwise, I might be convinced that I've solved the problem more efficiently, but in fact, I've actually got the wrong solution. And now that I'm done, this will just return the time it takes to do the recursion, and then the time it takes to do the naive implementation. And I'll just have a quick little table, call it trial table, that returns table results for comparison. And, well, it won't return it. It will output table of results for comparison. Let's start with 2, and we'll go up to 8192. And we'll see the result of these trials. And I'll just print them out so we can see them quickly enough. And what I'm hoping for is that we should see noticeably different performance when I'm doing my recursive versus naive implementation. So when I do my table, what we can see is on the left-hand side, this is the recursive implementation. On the right-hand side is the naive implementation. At first glance, it looks like the recursive implementation is 3 times faster than the naive implementation. That's nice. It's a very quick observation. We've taken something that looked like it was a problem that couldn't be made faster, and we have indeed made it faster. Now, some of this is through the power of recursion, and we also recognize that this naive implementation, namely taking n numbers and multiplying it by itself, that's really not what I should be comparing against. After all, Python has an operator that lets you raise a number to any power you want. It's the star operator. So I really should be using that one, and that's what I'm going to do now. Let's change this slightly. So instead, my check 2 is not, as you see there, it's base raised to the power of t. So this is what I want to do now. This is a fair comparison. What we'll see is that my recursive solution won't fare as well because, after all, Python has highly optimized code inside to be able to do these operations very quickly. I'm going to make my number of trials go smaller because this is taking a little bit longer than I'd anticipated. Let me just only go up to 2048. The overall growth pattern will still be the same, but I won't have to worry about letting it run for longer than it needs to run. So let me terminate this and then restart. So now that I've taken my implementation and changed it to be a more appropriate comparison, let's see what my results are. Well, now here, my recursive solution is about twice as slow as the implementation that they have. This is not surprising because, after all, what they have done, and if you look at the source code for Python, you can find this out for yourself. All the operators in Python are highly optimized C code that have been ported to different architectures. And so this implementation of exponentiation by squaring is fundamental. And they've already implemented it in C, which means that their highly tuned native C code will always outperform my recursive interpreted code. But that's okay. At least I've demonstrated the ability to take an algorithm and break it up and improve its performance. Let's take this one step further. And the reason why I want to do this is because this is, again, one of the things that happens in actual implementations. I'm not just concerned about raising some number to an exponent. It turns out that there's another operation that is quite useful in cryptographic circles, which is you want to raise a number to an exponent, and then that whole result has to be computed modulo some third number. You've seen the modulo operator already. This percent just checks quickly to see if the number is even or odd, but that's because it's checking to see what the remainder is when you divide by 2. You may find a need to do a modulo operator with a very large base and still compute its remainder. So what I'm going to do is take this exact same function here and make a small change to show how this would work with modulo arithmetic. And I'm doing this for a reason, because toward the end of this module, there will be an exercise with regard to prime numbers where this constant would play a role. Modulo sum m. So now I'm going to have raise x to the nth power modulo m. Each of these still applies. Don't forget in the base case that if you want to return x, you still have to remember to modulo m so that I don't return by mistake a larger value. Here, my recursion changes slightly. I still have to compute x times x, but I can do that modulo m, and then the whole operation can be done modulo m. And finally, when the exponent n is an even number, I just recursively call exponent mod. That whole thing has to be modulo m. So it's a small little change, and all I'm going to do is make the change over here. And one of the things that Python has is a function called POW, which allows you to raise a number to a power. So we've seen that already, but it's able to go further than that. You can raise x to the yth power modulo a third value. So I could say, what's 2 to the 13th modulo 2? And it's going to be 0, because in fact that's an even number. And so to really compare these two side by side, I'm going to arbitrarily say that my base m, it doesn't matter what it is, I'll call it 17. And I'm going to raise base to the t power modulo that number, mod. And I'll do the same thing over here, where I'm going to say power of base to the t power with that same modulo. I'm going to save this and run this one as well. And now I notice I need one more operator, which is here. Don't forget, in the exponent mod, I have to pass my modulo in through, otherwise it won't actually have it. I'm going to try that again. And then one last one here. I need to pass in how many trials I want. Oh, I should do trial table. That's right. So here's my table. And once again, I'm producing my recursive value here. And this is the built-in one over here. And you can see now I still can't come close to its internal implementation. But I've at least set the stage for a discussion point on how to do primality testing, and that'll be a discussion we'll get back to. So now that I've demonstrated my mathematical algorithm and I've shown how you can use it for a number of problems, let's shift gears and take this back to a different mathematical structure known as matrices, and we'll see how this exact same algorithm will apply there as well. So let's go back to the slides. This discussion about exponentiation by squaring seems to work for numbers. Can we use that same approach for others as well? The answer is yes, and now we'll actually be able to derive some really impressive gains in performance. Matrices are a mathematical concept, but they're used exclusively in engineering to do vast computations. And oftentimes, it's the performance that you get by multiplying matrices together that tells you the performance of your overall behavior. A matrix is a two-dimensional structure. You can view it as a set of rows and columns, each one of which has an individual value. I can take a matrix and I can multiply it under certain conditions with another matrix, and then produce a third matrix from that. Now, when a matrix is square, that is, it has the same number of rows as columns, then when you multiply it by itself, it produces another matrix with the exact same structure, just different values inside. So it turns out there's a fundamental need to be able to take a matrix and raise it to the nth power, just like we did with integers. Wouldn't it be nice if we could take this exact same approach and apply it to matrices? The good news is that you can, and more importantly, in doing so, I can demonstrate how the real performance of this algorithm can be revealed, because the basic Python implementation has no provision for optimizing the exponentiation of a matrix. So let's go to the code. To start with, I need to write a small function to create random matrices on demand. A matrix, as you know, is a two-dimensional structure containing rows and columns. There's a library provided with Python called NumPy, which is exceptionally powerful for doing all kinds of numerical calculations. And it's the place that you should turn to first when you're trying to solve a particular mathematical algorithm. It could be that it already has what you're looking for. In this case, I need to start with a random matrix. And so what would that be? It's a structure that is provided for me by NumPy, and I'll show it to you first, and then hopefully we'll understand the structure shortly. If I just want to create a random matrix, 2 by 2 random matrix, I can see that it's done using an array structure that is provided for us by Python. And you see here, as it's laid out, it has 2 rows. Here are the first values in the first row. These are the second 2 values in the second row. In this case, I just want a random matrix drawn from the number 0, random numbers between 0 and 1. This structure now is a matrix. And if I have that matrix, I can do a number of calculations with it. I can take that matrix and I can multiply it by itself. In NumPy, this is done using the operator dot, which will take a matrix and multiply it by another matrix. As you can see, when you take a square matrix and you multiply it by itself, you get another square matrix with the exact same dimensions, which suggests that I should be able to take a matrix and multiply it by itself n times. So once again, I'm faced with this idea of exponentiation by squaring. I can go back into my code and I can take the exact same structure that we use for our exponent, and now in this case, I'll do matrix multiplication. And here's what that would look like. This is my exponent mat function that takes a matrix x and raises it to the nth power. Now to do this, I need to change my base case slightly because after all, it's no longer a number to be raised to the power of 0 or 1. It's a matrix. But that's all right. The one case is already handled. If x is a matrix and I raise it to the first power, I just return the same matrix. It's done. This one's a little more complicated, but it's not as hard to understand. To raise a value to the 0th power, if it's a number, it becomes 1, the unity number, or the identity number. Well, in matrices, there's a concept known as the identity matrix. And so I want to return that instead. Number pi, identity. And the identity is based on how many rows there were. If I had a 3 by 3 square matrix, then the identity matrix is itself a 3 by 3 square matrix, where every value is 0, except for the diagonal running from top left to the bottom right. This will satisfy the base case of my recursion. And again, in case you've never seen that before, what's the identity matrix? I've got a 5. It's a 5 by 5 matrix where I've got 1s running down the diagonal. This is my base case because if I have a matrix and I multiply it by the identity, I get the same matrix back in return. And that way it plays the same role as the 1 does. So now I only have one change to make. If I'm looking to raise that matrix to an odd numbered power, I have to multiply x times the recursive call. It's a little more complicated because I take that recursive call and then I multiply x by it. So a way to look at this would be to say x dot the exponent. And what is internal here is x squared. But again, I can handle that by saying x dot x. This will satisfy the recursive call. And I need to make one last change over here, which is if the power of n were indeed even, then I can take the matrix and square it first, and then raise it to half the power. This becomes x dot x. As you can see, the structure remains that allows me to take a problem and recursively break it up into a recursive call and the base of the recursions. Everything else looks pretty much the same. Now I want to compare the trials to see how this would look like. So I'm going to go and modify my compare trials. I'm just going to copy all this because I want to keep it all here for you. You can look over on your own. Compare trials matrix and trial table matrix. Here, I'm not going to be doing, well, maybe let's do it. Let's see how far I can go. The powers are going to climb up pretty fast, but I'll see how far that goes. In this case, I'm no longer going to have a base number. I'm going to have a base matrix. So let me create a random matrix. And what should the size of that random matrix be? Well, I think this is where the real power comes in. If you have small matrices, to multiply them together, it's not that many operations. But when you have a matrix of 10 by 10, 20 by 20, it starts to significantly add up. So let's do that. Let's imagine that I have a size of my matrix as initially a 33 by 33 matrix. It's quite a good size. Now, I'm going to compute a number of trials with that size. And now the only thing I need to do is compute, in one case, it's the cost of raising, using my exponent mat function that I've just written, raise that base matrix to the power of t. And the other time, well, I've got to do a manual operation, just like you saw me do before. So I start with the identity matrix, which is a numpy identity. And I need to multiply it by itself, as we've seen n times. So it's equal check2 is check2 dot the base. And when that's done, now I'm finally faced with a discussion point. As you can see, I'm dealing with floating point numbers. One of the hallmarks of a floating point number is that it's an imprecise way of representing a value in fixed floating point style. And so when you're trying to compare two numbers that are the results of floating point calculations, it's futile to try to identify the exact value of the computation. Because if you multiply three numbers in a different order, sometimes you'll actually end up with a slightly different result. And that's the nature of floating point calculations. All that it guarantees you is that the relative error of the calculation is bounded. It can't guarantee you that it's the exact same result. So what I'm going to do is dispense with my ability to check, because I can't, and I don't want to have that be thrown off. And instead, I'm just going to return the times that I get. So in this framework here, let's discuss how this runs in the context of a trial that goes from 2 up to, let's start off smaller just in case it takes longer than I anticipate. Now, with a trial of 512, that's still pretty large. I'm taking a 33 by 33 matrix, and I'm multiplying it by itself 511 times. So this is a rather significant computation that might be needed for any number of linear algebra or matrix computations. And I'm trying my best to see if I can find a way to improve the performance of that. And so let's look at my trial table matrix. And I need not n. Got to find where the n is. It's right here. It's my number t. So how does this look? On the left-hand side, I have the recursive solution. On the right-hand side, I have the naive solution. If you're raising a matrix to the 512th power, as you see there, it takes about 4.5. But I only do it with recursion in 0.06. That's about a 900 times improvement. That's the power of taking an algorithm that would otherwise have been linear and converting it into log n. Or similarly, taking an algorithm which would otherwise be n squared and turning it into n log n. Anything you can do to break these algorithms so that they work on efficient problems, you can work on larger problem sizes where before you didn't even attempt them because they were intractable. So this concludes this discussion about the use of a recursive algorithm to perform exponentiation. I've shown it to you in the context of integers as well as two-dimensional matrices. To finalize this discussion, there's one more point that's worth talking about. And it's the concept of recursion itself. There's always a lingering concern that people have when they look at recursion, is they say to themselves, well, clearly this can't be the most efficient way to solve the problem because it looks too academic. It looks like it's almost mathematical. And there was a long time there that programs were trying to find non-recursive solutions for what otherwise would be a recursive solution. And the thing is that you can do this. And it's worth discussing how you would do it and then why you would do it. If you look at this particular exponent description. You notice that it has a very specific structure, and it's called tail recursive. This function does some computation at the beginning, and then at the end, if you note, whenever it calls exponent, it's the final thing that it does. And that notion of tail recursion means I should be able to find a way to take that function and convert it into a while loop. And that's the basic idea behind trying to optimize a recursive function and turn it into a non-recursive function. When you have recursions that are deep, that is, they call themselves 5,000 times, you have no choice but to do this because of the nature of the way Python is interpreted, for example. It will stop after about, I don't even know, it changes from one operating system to the other. After 1,000 recursive calls, it will stop and say I've run out of space to do the recursive call stack. And so programmers tend to think about ways to break that recursion and turn it into a non-recursive one. What I'm going to do is show you the non-recursive implementation, and then we'll put them side by side, and then ask ourselves a very simple question. Was it worth it? So let's take this exponent, and we'll make a non-recursive version of that. Now the thing is, this is still the same algorithm. All I'm doing is changing the specifics of the implementation. So I still want to get the same behavior, but I want to try to improve on the constant. That's the phrase you might hear someone say. I still get the overall behavior, but I want to make it more efficient in specific problem instances. So let's handle it. If n is 0, I still return 1. If n is 1, I still return x. Otherwise, okay, now I have to do some kind of loop. And since I'm going to be doing some exponentiation, I'm going to start with a value of 1. I'm going to do some looping here. And then when I'm done, I'm going to return the value that I computed. So let's try to figure out what it is that I need to do. Well, each pass through, you might notice a couple things. If n is odd, I know I need to multiply by x before I do the invocation of the exponent. Otherwise, I just do x squared and I go on. So I can make a very small observation. If value is going to be building up my product, I know that if the exponent that I'm concerning with is in fact odd, then value has to be multiplied by x. And I decrement my exponent because I now know I've handled that one. And I make forward progress by saying, you know, now I'm interested in the next problem size where n is 1/2 the size. And if you notice in both these cases, whether it's the odd recursive invocation or the even recursive invocation, I'm calling exponent with x squared. So all I do is take x and say, well, you know what, x is now itself squared. So now I have raise x to the next power, and I go back to do my while loop, and it will terminate. So this looks good. Let's see what it looks like from the point of view of performance. Have I done anything to materially affect the performance? Now, at the outset, I'll say that this can't by itself change the performance of the algorithm from n squared to n log n, because all I'm doing is just a minor implementation tweak. But it could have a performance impact, and so let's look at that. So I'm going to come up with this compare trials function. Now what am I comparing? I'm comparing the recursive versus the non-recursive. So compare trials non-recursive. This is going to be my recursive invocation, which is base raised to the tth power. And then this is my non-recursive base raised to the t power. In both cases, I still want to check, because this is an integer, and I'll return my time. So I need to have a trial table to go along with that. Put that back up here at the top. This is my non-recursive trial table for comparison, for comparing non-recursive, recursive. So I compare the non-trials. Sure, go up to 248. That all looks good. Let's try it out. Make sure that it's the operator star equals. Oh, I need my trial table. So once again, on the left-hand side is my recursive call. On the right-hand side is a non-recursive call. It looks like the recursive call still handily outperforms. But there's one little trick. The very last time through this while loop, I may be multiplying x by itself one too many times. And does that matter? Well, it certainly does. If I'm trying to raise something to the 80th power, that's a very large number. So I can prevent this by just saying, if I have any more to do, only then do I multiply x by itself. It's a little extra step there. Let's see if it has an impact on the trials. And it looks like that by itself has just edged it out. So I get to save about 20%, 10, 15, 20%. Was that worth it is the ultimate question you have to ask yourself. Was it worth taking a simple, elegant, clear to understand function and turn it into a convoluted, hard to understand, hard to maintain, iterative while loop? Most cases the answer will be no. But it's still worthwhile understanding that if someone comes to you and says, oh, you have to find a way to break that recursive implementation, it's going to be so inefficient. You can try to explain there will be ways to remove the inefficiencies naturally, but you're not going to get a massive improvement. You're going to get a targeted improvement, no more than 15, 20%. And maybe that's what you need to do if that's a highly exercised part of your code that needs the most possible improvement. But in most cases, you'll find that it's not required or necessary. So now we've finished the exponentiation by squaring. We've shown you how to do it in recursive structure. We've shown you how it applies to matrices. And then I finalized this with a small little side discussion on the nature of trying to remove recursion and whether it's even worthwhile to do so at all.